Well, it's really a pleasure to be here for the 80th. As am I? No, the first. Yeah, it's up. I'm sorry. For the 80th, I mean, it's always hard following Michael Rabin. I'm glad there was no opportunity to ask him questions. And, it would have been fun. I've known Michael a really long time, and I know Dick a little less. I want to say something about that. The one thing, Michael made a comment about the 90th, and I'm sure we'll hear more of those. I'd rather say to Dick that your initial career is really going well, and I look forward to you to continue for the rest of your career to do at least as well. So, good. So I first met Michael. Are we flipping correctly? Yeah. Is that coming up? Oh, I see. We did this on my machine, and now it's running on this machine. Can you read this? Does it work? Okay. This is the fear of moving from one machine to another. All right, well, let's see if it works. I can do it without slides. So anyway, what happened, well, I think the first conference I ever went to was a thing called IFIPS. Has anyone even ever been to an IFIPS? Yes, a couple, right? Okay. So I knew Michael actually from grad school, long story why. At IFIPS, I pulled out a couple of papers. You notice one is by Michael Rabin. I still remember the talk. Michael gives such fabulous talks. It was on impediments to AI, essentially talking about work on logical decision systems, very neat. You also may notice that there are only, as far as I can tell, 4 talks at this very large conference. And it was a chance I got to meet Dick Karp, of course, who already knew Michael very well. Okay. For a talk like this, I didn't want to make something very technical, but I wanted to talk about, at least, I didn't know you were going to say that, but this work that Dick and I did, maybe in a little bit of some extensions. And hopefully you'll enjoy that. So this is coming out really, should we ship? Is there a way to, no. Can you help? Or we could use my machine, it's right there.
Yeah, why don't we go ahead and do that?
Sure. Terrific. Can you? I was reminding Dick that one time he came to Georgia Tech before I was there to give a keynote, and he worked on the airplane making his slides because it's a long flight to Atlanta, and that's, we all do things like that. And then he got off, and we were taking him to lunch, and he was going to give the keynote right after lunch to a probably even larger group. And he said, I tried some new pens on the plane, on these old acetates. He said, they look a little faint, but I'm not really sure how it's going to work. And I'm thinking, oh my, let us all hope. He gave a great talk, but the slides were invisible. So I guess I can do the same. So let's see if this works. Oh, that's better. Okay, thank you. So bad joke, but it's his 80th. Okay, I guess we only have to add a few more bits as time goes on. Does that help? Okay, and these were just some random pictures of Dick over the years. I thought I was going to throw a couple of ringers in, but they really aren't Dick. Okay. And again, here is, you can see there's Michael's talk. That was really great. One of the other stories here is there weren't very many theoretical people talking at this very large conference in Sweden, and that's where I met Dick. So, okay. There's this thing called Karp Lipton that I guess you mentioned, and you probably all know this, but the theorem basically is, the way I used to say it, is if satisfaction is easy, if it's got small circuits, then we get this collapse of the polynomial hierarchy. What I always thought was interesting about this, and would tell my students, is that I read a number of papers, I may have even written some of these, where in the introduction we would make throwaway remarks And the introduction is a really interesting part of the paper because you don't really necessarily think it through, right? Your theorems, I'm sure you get right, you think through very carefully, you try to prove the theorems very carefully, but sometimes in the introduction and maybe the conclusion, you just throw out something. And we've made mistakes there over the years. And I remember at the time, there were a lot of papers that said, well, obviously, if something has a small circuit, there's no way to get an upper bound in a Turing machine uniform model, because you can have undecidable theorems, languages and all sorts of such things. But of course, the trick here is that SAT is special. And I want to talk a little bit about that. Not so much that you don't know this result, but you'll see why. Okay, I want to just do that. There are two other things in this paper. That's why I want to do it. One is the famous notation of a complexity class / the advice bits. I assume lots of you know this notation. This is really due to Dick. I mean, it's a joint paper and joint results, but he wrote the draft that included this. I thought it was very brilliant. We don't get any money for the use of this. We did not trademark it, even though I have a trademark. I guess that's probably illegal. I wish we did, but maybe we could have a PayPal account and you can all send us a nickel every time you use it. That would be great. There's also another cool part about this paper is there's a whole section you've never read. Probably you've never read the paper, right? I mean, everybody knows this result probably, right? But I suspect a lot of you have never read the actual paper. Indeed, when I looked it up on the web, I couldn't even find my own copy. But if you've forgotten the proof, here's some help. At the complexity meeting in 2010, they had tote bags that had essentially the proof of our theorem. Now, I remember when I heard about it, I wasn't actually at that meeting, unfortunately, but when I heard about this, there were several things that went to mind. One, your life's work is on a tote bag. So is that really good? I mean, maybe that's really good, or maybe that's, I don't know, maybe that's really bad. I mean, the other way to look at it is, again, did we have some copyright position here, Dick, where we can, I mean, they printed 200 of these without my permission anyway, but okay, we'll let it go. All right, obviously I need at least one proof here. But here's the original paper, here's just a little piece of it. And for a variety of reasons, the main theorem we sort of pushed aside. We had this other whole section we called round robin method. And it really wasn't about SAT, it was about something else. And probably, I don't want to show of hands, because people will never do that. But I sort of forgot about this, and it came up in an interesting context. And that's the rest of what I want to present today. But the round robin method is a whole big section in this paper. Dick, do you remember this? No, he doesn't remember. Okay. And if you notice, this is not even, anyway, it's not a LaTeX. We apologize to Professor Knuth for that, but it was a little early in the years. Okay, the whole idea there was, of course, we had something like this. We were thinking about chess. I'm sorry, today we're going to think about chess. We were thinking about, obviously, generalized games. If you like, think about a game that's piece space complete, pick your favorite game. Obviously, 8x8 is not, but in general, chess is. And the idea is Alice has two different Bobs that each claim to be very good players at her disposal. And obviously, we're computer scientists, two is really make it n, so she may have many of these. And her job is to use these players to win this position, which let's assume that she's white and it's a winning position for white. Just assume that. And she wants to know what to do. But the point is Alice is not a chess player. She's not very good at that. So she has the advice of her two experts. So you all get the sort of general setup. I guess it's some sense related to work, I guess we'll hear at the end of the conference from Manny Blum on what humans can do. But it's sort of, we don't want Alice to cheat by saying, well, I'll run an exponential search. She's got to do something really simple. Is everybody sort of with me? So the deal is Alice basically can use her experts by running, it's sort of an obvious thing, but I guess we did it first, running a round robin tournament and trying a move and then using the players against each other. And the assumption is she's told that one of these players is perfect and the other players may be very good or very bad or terrible or make some mistakes. And the deal is, her job is not to discover who is the optimal player. It turns out I don't think she can do that. In fact, I'm sure she can't. And we actually say that, I think, in the paper, something like, there's a curious, subtle point that you can't actually figure that out. But you can figure out an optimal move, right? And you play them against each other. It's not all that difficult. All right? Everybody happy with that? So Alice wins. I'll just leave it with that. But things have changed today. So leaping forward a few years, chess is now, lots of people are interested in computer chess. So I've worked a lot with Ken Regan in my blog and elsewhere on chess. So that's what we're going to talk about, sort of building on that old result, trying to do something a little more modern. All right? Okay. Now, when I first heard about this, in my head, you should know, and I'll give you some more data, but computers are much better than humans. And I don't mean everyone in the room, assuming we don't have some very strong players. I mean everyone on the planet. Computers no longer can be defeated, at least in a long enough tournament. They're just not going to lose to chess machines. But it's not, I guess the picture I've drawn, or not drawn, but copied, is a supercomputer center, maybe worth $100 million, with lots of computers. That's what I always thought, but it's actually this. It's your smartphone. And probably in the future it could be your light bulb, or it doesn't take that much computing power running the state-of-the-art algorithms that you can get either free or for modest amounts of money on the internet. They're very, very well optimized. They do alpha beta search, they do other tricks, but they just can't lose. And you don't really need much computing power. Matter of fact, as an aside, they actually don't know what to do with more computing power because they start to run into problems. In other words, if we go back to the supercomputer setting, they'd love to run on that if they could, but it doesn't parallelize very well. It's one of those interesting problems. So they really are running mostly single core or very few core. So here are some numbers for you. And I'll just put this up. Yeah, so, well, that's good. There's a rating in chess, maybe everyone knows this, ELO ratings. It's I guess, anywhere from around 1,000, although you can be lower, up to into the 3,000 range. No one's gone beyond that, either computer or humans. This data is a little older, but from Ken, 2850, I think, is roughly what the world champion plays at, although he's actually not been playing very well lately, but that's another story. Humans do have sometimes get distracted or make mistakes or get tired. The computers don't. When this was collected, the computer engines running the standard algorithms were playing quite a bit better. And the way to think of this rating is if you're a couple of hundred, I think it's about 3, above someone else, you basically should win on most of the games. You should win about 75%. So that means, maybe Magnus, the current world champion, could play one of these engines. He doesn't want to. Maybe he could win a game, but if he played, 20, he'll just be destroyed, and it's no fun. So they don't do it anymore. One side effect, if you read our blog or talk to Ken Regan, is this makes cheating a huge, huge, interesting problem for chess. Because if this was a chess tournament and we were about to pair off for the first round, if you've got a laptop in your pocket, I'm not suggesting you would cheat, but maybe. People sometimes go to the restroom. They've been caught with machines behind parts of the restroom accessories, shall we say. They sometimes have had friends in the audience, doing like first base, third base coaches giving hand signals. There are lots of ways to cheat. Apparently someone was caught with something under their arm. I know it sounds kind of a little gross. Anyway, but if you can get, some bits to you, you can play really well. And one of the things, I'm not going to talk about Ken's statistical work, but one of the things that he's been doing a lot, and you should either invite him or read some of his stuff on our blog. He tries to do statistical analysis to see if you claim you're a 2300 player, but you're actually playing a 28, for too long a stretch. So they're very interesting, actually, machine learning and statistical questions that he's still working on. All right, so how do you beat the machine? So people had this idea. I decided not to include the cartoon. I don't know why. They like to call them centaurs. Like it's part human and part animal. I don't know. It should really be part machine, part human. So the deal is this. What if you have access legally to a computer like this one, which is more than adequate to play? Today, I think it's certainly in the low 3,000 range. Can you, as a human, with this machine, play better than the machine? And they've done some very small experiments, not a lot. Ken says yes. The data I have here is from an old tournament where adding the human added about 100 points, which isn't a huge amount, but it's not obvious to me why it wouldn't be worse. I mean, actually, when I think about it at first, when he told me this, I thought, well, wait, if I have access to a computer, I mean, I'm really a weak player. If I tell the machine, no, don't do that, I think, this is a better move, and then it's sack mate, that would be bad, right? I mean, so why do humans help? And the answer, I think, is not well known, but not understood yet. But certainly one possibility is that machines are really good at tactical stuff. Don't ever get in a situation with the computers where what they're doing is basically tactical. They're just going to kill you. But there are these interesting strategic positions where they just seem to get lost, even though they're looking 20 moves ahead. They just don't know where they're going. So maybe the human somehow could say something. And what got me thinking about this is we were involved in a big conference call about a month ago when we were up in Buffalo working together. And it was with people who are trying to organize these human-computer experiments to see if humans can be helpful to computers. And obviously, for chess, this is a general AI question, right? It would be really interesting. As we automate more and more things using machine learning and other tools, are we going to just hand it over to the computers, or are humans going to stay in the loop and maybe add value? And I think the answer is probably yes. So the nice thing about chess is it's a very well-defined, kind of specialized world, and that's what we're talking about. All right. So we're interested in that. So like everything, I wanted to think about a specific problem. So here's the problem I wanted to look at. So imagine you have Alice again, and it's the same position, although that doesn't matter. And I've drawn two chess engines. They actually don't use the arms very much at the high-end machines. It's just software. There are people that are trying to also pick the pieces up and move them. That actually matters if you play speed chess where the computers kill you. I mean, there's no chance. But of course, if they have to move the pieces fast, I think we still win because they tend to knock over other pieces, which is a bad thing when you play chess. So I know when Ken plays against these robot arms and he allows them to knock pieces over, he just gets killed. And he's about a 2400 player, which is international master level. So just below grandmaster. Okay, so you've got Alice, and she has access to, say, the 2, again, think 2, think n, but some number of these experts. It sounds like the problem we just, did in this section no one reads. So when I first thought about this, it sounds pretty straightforward, but, run the round robin. But I want to change things a little bit. This is a picture of Polio, so I was trying to think of the simplest problem that might be interesting. And the problem here is that what if Alice has access to these 2 machines, but I tell you neither one is perfect? That each of them make errors. And to make it the simplest problem I could think about, they each are going to make one error. By that I mean there's some position among the large, finite, but huge number of positions out there in chess where each machine will make an error. That is, if the machine, I know in chess you can win, lose, or draw. Let's just make it win or lose. Let's just make it simple for the moment. What I mean by that very precisely is if the position is winning, the machine in some position will make a losing move. All right? You may never find that position. It may be a trivial position that you would notice as a human. It may be some very complicated position, somewhat like the one I guess we had up on the board, on the screen. It may be something else. And the other assumption is we'll assume that the two machines don't ever make the error on the same place, like an independence assumption, which we do all the time. I have no reason to believe that's true, right? But we're more than willing to make that assumption. So the question is, can Alice still win? Can she win a one game? And the answer is now, if you do the round robin trick, I don't think it quite works. If you think about it for a minute, when you start playing them against each other, you don't know if they make mistakes or not, and I think you can get misled, especially if they make more than one error. But certainly, if they're both faulty on some positions, it seems clear that the old techniques won't work. So I don't actually know how to answer this question. And if you know the answer instantly, check your email or do something else and tell me later. Is that all right? So you don't embarrass me too much during the talk. Sorry, buddy. I don't know. Is it too early in the morning? Am I just really not funny? Okay. I mean, I'm sorry. Okay. Have you heard? I'll just tell some dick jokes now. No, okay. So here's what she can do. So I claim that one reason maybe we would have looked at this is, first of all, when we wrote this paper so long ago, errors, we weren't so much interested in things that were approximately correct, right? That's a more modern notion. So when we were looking, Dick and I, at Alice be given a collection of experts, we assumed one was perfect and the others, who cares? They made errors. Now we're looking at Alice is given a whole bunch of experts. The general case would be, and they each make some errors. But I'm starting with the simplest case with just two. And I claim that there's now a probabilistic algorithm where Alice will be able to succeed and win with at least some, I guess a quarter, at least some decent probability. Now you might say, well, that's not all that good. But notice if you take the machine and run it by itself against a perfect player, it might lose every time on this position, right? And each machine. So and notice, it's not that they make a mistake in this position, but they make a mistake later on. And how do you know that? Alice is not a strong player. So getting ready for this Karp talk, I wanted to do something linked to something we had done, and I thought I had a really clever algorithm for this that was deterministic and worked in the general case, and it fell through, so I'm presenting a probabilistic algorithm that at least does something. And I invite anyone who wants to talk to me or has a solution, to the general case we can talk about. But this seems like an interesting problem. And this, at least I hope you agree with that. Notice, it's a more general question. You have experts that make errors, so what can you do? So she has a really, maybe I'll just say, she has a really, really dumb strategy, right? Does everybody, you probably all see the strategy? So the strategy is simply, she just flips a fair coin and takes the advice of, one of the engines. That's it, all right? Really simple. The trouble with that, so I guess I can advance. The trouble with that strategy is the idea is that, in that position, they both might do well or they both might make mistakes. Well, they can't both make mistakes, I assume. But they may do different moves. They may not agree. Notice in chess, there's a very important point, that in a position there may be many winning moves. And there may be, of course, many losing moves. So if she does this and the game lasts, 50 moves, which is not uncommon, that looks like it could be some strategy like 2 to the minus 50, which is not also good. It's not that terrible, because if she simply made random moves, her strategy, because I think the average is about 20-some moves per turn. So if you just flip coins, your winning percentage would be almost zero. But 2 minus 50 is pretty small too. And the reason that works is, let's see. I guess I'm just saying that, I mean, this is a formal way of saying, she gets the moves from the two players, she flips the coin, she makes the move, and she goes on. So it's one of these, very standard things we see. This is like the babyest case, I guess you can imagine, where you have a really, really simple algorithm, and the whole argument, which is is also fairly trivial, is trivial. But it's a very simple argument, but I'll show you the argument in a second. The argument is that this doesn't do that badly, right? And maybe you all see it, I'll just draw a picture. So it turns out there really are, let me explain the notation. So the red dot stands for a chess position, and W and L mean you made a winning move or a losing move, okay? And notice you can't have an LL, because that would mean both machines made a mistake at the same position. So that's disallowed. Now, there may be ways around that, and indeed I thought I had a way, but let's, for this morning, leave that. So it could be you're in one of these. Of course, there's another flip. It could be WL or LW, so there are really three cases. But the critical point is if both machines have made a correct move, then Alice is in great shape because whatever, the coin flip doesn't matter. It doesn't matter how you win, you just have to win. But on the other hand, if it's a win-lose, when you flip the coin, you might lose. But the good news is half the time you do well. And of course, the critical last point is that every time you do that, because you're continuing the game could go on for many moves, is the advice engines are burning up their errors because they only have a small number of errors to get you in trouble. So you're not going to see that, you're not going to be really flipping a coin. Most of the time, that matters. Most of the time it will be a win-win, and every now and then it will be a win-lose. You have no idea, and Alice will do very well. Now, I believe, I think, let me just do one more, and I think I'm about on time. I think I can do a little bit better, like I can do the square root of this. So in other words, I don't just flip a coin, I do something else. So I'll do that offline or talk to anyone who is interested. For all I know, there's a deterministic algorithm that works perfectly in the case of, I guess M is the number of errors. But right now, I can do a little bit better. But in there, I can't have Alice just flip a coin. I have to have her do some investigation and try a little bit like the round robin, try the engines against themselves and gather some information so I get a better bias on my coin flip. So, that seems kind of interesting. And it's back to the beginning where we started, where you're playing against these experts, but now we allow errors. And, Ken and I have thought of even doing some experiments with real engines to see if you take this and play two engines against a third, will they actually do better? Because you're sort of somehow getting around their mistakes. And obviously, it would be really neat if we could do something like where the engines make epsilon, epsilon fraction of positions, they make an error, and prove something along those lines. And hopefully, we'll have that before the 90th meeting for Dick. And I guess I'll stop. I think I have a minute or two, or a few seconds anyway, for some questions. Thank you very much. Oh, time, yes.
So I'm supposed to believe that Alice can do the sum of the 1/2.
Yes. Thank you. So the question was, we can at least do, with just the two errors. There's a way around that,
That's what I was going to propose, but I found a flaw in my argument.
Well,
I mean, okay, so for example, she gets one coin flip.
yeah,
So maybe she says, okay, I'm going to stick with this guy. Because he only makes one mistake, and so I follow all the way through.
right.
And I'm sorry.
Oh, I'm sorry. I thought if I could repeat what you said. But so you just pick one of the engines and say, I'll trust it.
Yeah, right. But I realize that doesn't work because sort of whichever one she tried to go with, she might still wind up losing.
She might hit another
Yeah.
pothole. Yeah,
Right.
yeah,
Okay.
exactly.
So,
Right.
But you do have a way to get around it with only
Yeah, you
one
have to have
question?
some communication. I can talk to you,
Okay.
certainly feel thrilled to do that. Oh, is there, maybe I should keep away from this for feedback? Catherine?
I'm Dick's partner, so I guess I'm biased. But I've been living with this chess and not having been a player, so it's kind of all foreign to me. But I wanted to ask you, can you generalize your findings about chess to other high-risk behaviors in other realms?
You were supposed to ask what happens. A combinatorial friend of mine once told a partner, always ask at a graph theory conference, what about the countable case? Where everything's always finite. Thank you, Catherine. She knows that it's like a planted question. I guess I didn't expect that. So maybe that's not planted.
It wasn't planted. It's
It wasn't
completely
planted.
spontaneous.
Okay. The answer is we're using chess as a kind of metaphor in the sense it's well defined. It has fixed rules. There's a lot of data. One of the cool things is Ken is collected literally every game ever played that is recorded. In tournaments, so he's got 5 million games or something in the last 100 years. But we do view this as potentially using experts in other, maybe more practical. Chess is kind of cool, but there's not really a lot of money in chess, for example, a lot of impact, perhaps. So maybe if you have experts that make errors in other situations, can you do better than what Don was saying instead of picking one, which is sort of what we tend to do now, right? We hire an expert or pick a program and use it or build an expert system. But what we're talking about here is maybe having separate ones. And by the way, there is I'll just end with this. There is real data back in chess that there are a whole bunch of very strong programs, and they do make mistakes on different positions. I mean, they have examples where one of the machines, one of the programs will blunder, make a mistake in this position, the other one won't. So there's actually some experimental data on it. Thank you. Is there anything else, or I think I've used up my time anyway? Well, thank you again. It's a real honor. Do well, Dick.